Right, so first lesson for the energy unit. I'm going to just start with work, and I'm going to see how far I get in 10 minutes, then I'll stop the video and perhaps make a second one to follow up. So, just enlarge this. To start off, the first thing I'm going to say is whenever you're doing anything like this, whenever you're watching any of these videos, as I said in class, first thing you want to do when I set up a problem, when I put a problem on the board that I'm going to solve, you should try to solve it yourself first. Okay, so anytime I do that, I'll try to remember to point that out as I go. But always try, when I put a problem on here, try to solve it yourself first. Second thing, remember to pause and try every step on your own. So what I'm saying there is, when I get to each step, if you've already done the step, keep going. But if you haven't done that step yet, pause the video and try to do that step yourself to see if you'll know where I'm going and what's going to happen next. And finally, whenever you're doing any of these problems, always try to follow the 7-step method. I'm going to try to model it when I do it so that you can see how I expect you to do it. This will get faster. It's slow and tedious at first, but it helps you make sure that you understand the questions. It'll get faster as you practice. So right now, you can pause and open to this question. It's in the textbook. It's one of the review questions on page 229, number 3. So here's the question. A child pulls a wagon by the handle along a flat sidewalk. She exerts a force of 80 newtons, at 30 degrees above the horizontal, and moves the wagon 12 meters forward. That's along the ground. And the force of friction on the wagon is 34 newtons. So it's asking for the mechanical work done by the child on the wagon. So for part A, we start with step 1. Step 1 is find the target. It's asking for the mechanical work done by the child on the wagon. So work equals something newtons. We can think of it as a vector if we want, but right now we just have to do it. We'll still be able to get the answer this way. So step A. Step 2, draw a picture. So step 2, we're going to draw a picture of this. We have a wagon on a flat sidewalk with forces at angles. So here's the picture. She's pulling at an angle of 30 degrees above the horizontal. So that's 30 degrees and 80 newtons. And she moves it. I'm going to do this in a different color so we can leave that as a free body diagram. 12 meters. And finally, the other force acting on it is 34 newtons. Friction acts in the opposite direction of motion. Therefore, it's 40 newtons this way. Now, we could take a look at this and think about a few things. One, it's possible that the 40 newtons is the same. It could be just going at a constant speed. It could be accelerating. We don't know. And for the purpose of calculating the work she does on the wagon, we don't really care. So when we're trying to figure this question out for part A, we have to worry only about what we care about. But I'm going to leave this diagram. We're not going to use all the information in this diagram, but I'm going to leave it because for part B, we will use the other part. So, her work done on the wagon, very, very simple. We have the given information. I've written various values in where they apply, and we're not given the mass of the wagon. We don't need it. Step 3, given information. Step 4 is find the formulas. The formula that works for this, work is equal to force times displacement cosine of the angle, where the angle is what angle the actual force is from the direction of motion. And we have all of these values. We have 80 newtons. We have a distance of 12 meters. Make that really clearly newtons. And we have cos of 30 degrees. So pause, punch the numbers in, and see what you get. So I get a total work of 831 newtons, or joules. Sorry, not newtons. Work is in joules. Did I do that up here too? Yes, I did. Okay, and significant digits, we're given 3, 3, 2, 2, so it's 2, so that's going to be 830. Part B, it asks for the total work done on the wagon. Now for the total work done on the wagon, we want the total force or the net force exerted on the wagon. So let's put part B over here. We can use the first parts for this from this solution in this solution.
Stop call 227, please. Mr. Stop call 227, please.
So when we want to get the net force done, it's the net force in the direction of motion. We have 80, so net force is going to be 80 cos 30 minus 40. Punch that into your calculator. 30 cos times 80 equals minus 40, 29.28 newtons. And now our new work in this one is going to be F net times the displacement. So we're going to take this number and put it here and multiply it by 12, which gives us 351 joules, or a network of 350 joules. All right. I should point out that the textbook gets 420 joules here. I would love to hear from anybody if they can figure out how the textbook gets 420, because I get 350 and I'm quite certain that I'm correct. So if anybody can show me how that worked, I'd appreciate it. Okay, next part of this question, I'm just going to do a quick derivation of the kinetic energy formula, and then we'll go to another video to do the to work with kinetic energy. So here's how we get the kinetic energy formula, 1/2 mv squared. We're going to start with this equation right here. And the question, how much work did it take to increase an object's speed? If you remember, conceptually, that's how we decided what the kinetic energy of the object was, because work is energy. So if you put a certain amount of work into an object to change its speed, then the energy it has because of that change in speed, or the energy that it has because of its speed, is equal to the work done. So if we want to work, let's start with a general equation, this one here, v2 squared equals v1 squared plus 2ad. And I asked the question, why do we choose this equation? Pause the video now for a moment and see if you can figure out why, and then I'll explain. We choose this equation because we know that work is equal to force times distance, right? Or force times displacement. We're using distance for this just to keep the vectors out of it and make it a little simpler to understand. We know that it equals force times distance. Force can be associated with acceleration from Newton's second law. Force equals mass times acceleration, or acceleration is force divided by mass. Therefore, acceleration and distance are two of the values we're going to want. We're talking about a kinematic situation here, constant acceleration, and we're talking about changing an object's speed from v1 to v2. So this equation uses all the values that we want to have in it. Now, if we want to figure out how much energy it takes to change the object's speed, then we want to know the amount of work done to change the object's speed. So I'm going to rearrange this equation to get the change of speed on one side, v2 squared minus v1 squared equals 2ad. Now we know acceleration is force divided by mass. So I'm going to replace acceleration with that value. 2 force over mass times distance. Once I have this, I can rearrange my equation by doing some algebra on it. If I'm multiplying on the right side by 2, and to get rid of that, I have to divide by 2. And on the right, so that gets rid of my 2. And if I'm dividing by mass, then I have to multiply by mass. So when I rearrange this equation, once I've canceled these values out, let's use a third color and make this really clear. So the mass is canceled. We are left with m v2 squared minus v1 squared over 2 equals force times distance. Well, we know that force times distance is equal to work, or energy. The other thing we can do, this is the change in kinetic energy, and this actually applies to the work kinetic energy principle. But this equation is also useful if we decide that our initial speed is 0. If we want to find out what the energy of an object is when it's moving, then all we have to do is figure out how much energy it took to get it moving at that speed from a speed of 0. Which means, if we cancel this value out right here, because it's equal to 0, we get...
Mr. Pajanovic, there's a call on 101. Mr. Pajanovic, call on 101.
We get 1/2 mv squared is equal to the kinetic energy. And of course, we can rearrange that. Kinetic energy equals 1/2 mv squared to get the equation that we're familiar with. So that should take you well into section 5.2.